Follow the link. No, that's not what I wanted. What? Is not it. Where did it go? How do I erase this? Can I just do this? You gotta be kidding me. Let's see. I can get to it another way. Good morning, everybody on Zoom. I'm figuring things out. Just give me a second. Y'all, don't even. No, there's no other storm. I don't know what y'all are talking about. We're going to pretend like it doesn't exist.
Really, we can all just be virtual, and either you make it, you make it. If not, it's fine.
Oh.
So every class gives us extra points just for stress. Yeah.
Just for stress.
Just for stress.
Okay, come on. This is what I need. Thank you. Okay.
They're all good. Only one of them, like the side of the panel, kind of down. So
Okay.
part of the shed kind of lines up next to the panel. Part of the side and shed.
All right, so I need to share my screen with my Zoom people. I know, y'all. It's like too many things going on. Where is that? One second. Attendance. Here. No? Okay, where does it go? Oh, here it is. I'm sorry. What is the, oh, we have a joke. Someone else is going to do the joke today. What is the most loyal element? I don't know. What is the most loyal element? Oh, I lost the chat. Here we go. Gold, because it doesn't share its electrons. Bromine. Oh, that's good. That's good. Bromine. I like it. I like it. That's good. Oh wait, no, don't do that. Don't do that. Okay, let me log into Clicker.
Well, everybody canceled their outpatient stuff because of the storm started. They're ready to try to catch up again.
Oh yeah.
So the nurses for them. I don't need a coffee.
Yeah, you do. You do need a coffee. All right, let's see. So I will go ahead and open this for attendance. So go ahead and check in on attendance. How many do we have? We have 34 today. Oh, start video. My video wasn't on. Oh, sorry, y'all. Did not know my video was not on.
Oh, go ahead. I'm sorry. Dr. B.
Yes.
My presentation was phenomenal.
Yes.
Thank you so much.
Look, I can help. I know a few things. All right. Did I tell y'all the peekaboo joke?
Yes.
I told y'all that one.
I shared it with my coworkers.
Did I tell you the mitochondrial one? Did I tell anybody mitochondrial one? No? Okay. All right. So I don't know if y'all know that Halloween is my favorite holiday. I don't know why. It just is. So In October, the mitochondria turns into the mitochondria and becomes the haunted house of the cell. Thank you, thank you. I really like it. Y'all are so sweet. Y'all are so sweet. Okay, so I need to open a few things still. See if I can move things around. All right, I need this one. Okay, so what we're gonna do today to start, I'm gonna hand out some papers. If you are at home, the papers are on Moodle. So if you go to Moodle, Here, if y'all wanna grab one. I'm gonna come around and give to everybody because I meant to put them out and I did not. We're waiting on Moodle, but it's in Moodle under Chapter 7. It's thinking about it. Chapter 8 is up. And for next time we meet, you only have to watch the Chapter 8 lecture, but the Chapter 8 Section 1 lecture, but I have 2 sections up. Oh, because that one I didn't put the right thing on that one? How did I do that? Okay, but it's here. All right, so if you scroll down, Chapter 7 here, enzymatic activity of chemotrypsin. That's the one we're going to work on right now. So you can follow this to get to right here, and that's what I'm going to hand out to everybody real quick. So here we go. All right, everybody knows how chemotrypsin works, right? You can walk through the steps. Yeah. Probably not, right? Probably not. Okay. All right, so there are a few questions. I kind of want you to take a second and to read these 3 questions before we play the video so that you kind of know what you're looking for. Now, I gave you a little bit of a cheat sheet. It didn't copy too well, but the picture's also on Moodle that has the individual steps as just the pictures without the words, kind of help jog your memory so you can write yourself some notes so you can figure out how this works. And then I put you the ultimate cheat sheet. It's the whole figure with all the words. But try not to look at that last page, okay? Try not to look at that last page. So I'm going to give you like 2 minutes, read the questions so that you know what you're looking for before we watch the video. The last page does contain the answers, Mohammed. This is Chapter 8. It's Chapter 7. It is Chapter 7, right? Yeah. All right, so where did I put that video? Yeah. Okay, so we're gonna watch a quick little video, and this should help to refresh your memory. I'm gonna minimize the chat. I guess I'll stick it right there. And don't forget to check in on Clicker for attendance. So this is just gonna kind of give you a quick refresher on exactly the big steps in chemotrypsin digestion. Okay, or enzymatic activity, however you want to think about it. All right, I don't know if the sound's going to work. Hold on.
Carboxyl group of one
Hold on.
amino acid to the amino group of another. Proteolytic.
Sorry, y'all. Got to figure all this out. Here we go.
A proteolytic enzyme, Trypsin, hydrolyzes the peptide bond, which connects the carboxyl group of one amino acid to the amino group of another. The Trypsin reaction involves two side chains at the active site, histidine 57 and serine 195. First, the serine attacks the substrate's carbonyl carbon, forming a tetrahedral intermediate, and then an acyl group bound to the serine, an acyl enzyme intermediate. One product diffuses away at this time. In the second stage of the reaction, a water molecule attacks the acyl enzyme, forming another tetrahedral intermediate to make the other product, which diffuses away.
Okay. How many intermediates did you see in there?
Proteolytic enzyme.
2. We had 2 intermediates, right? Do you remember the energy diagrams about what happens when you have a enzyme catalyzer reaction? Instead of having one big hump, what did we have? 2 smaller humps, right? Okay, so what do those 2 smaller humps signify? So lower activation energy, but you still have intermediates, but now you have 2 intermediates, right? That are of lower energy. So when we analyze this, because you're about to answer some questions and analyze how chymotrypsin works, I want you to think about that we're making 2 intermediates and that those 2 intermediates are low energy. So by the time we're done, I want you to be able to explain why those 2 intermediates are lower energy, because that's super important for enzyme activity, okay? All right, so let's go back to, stop it. Let's go here. Okay. So there are a couple of questions that I want you to try and answer. So I'm going to give you a minute, and I want you to try to answer them. Then we're going to kind of work together on them. So Taylor, we covered all of the sections, all of chapter 7. So we did some in class and the rest were for you to watch for homework, right? So you had just the last section to watch, section 5, before today. So technically today we have covered all the lecture. So today we are going to do some problem solving. Okay, Taylor? Great. Okay. So these 3 questions are what I want you to try to kind of answer. Okay, y'all think 1 more minute and be ready to join up? Okay, 1 minute. All right, y'all ready? Yeah? Okay, so what reaction does chemotrypsin catalyze? Don't everybody try to answer at once. What? Say again? Hydrolysis. Hydrolysis. Hydrolysis of what? Of a single peptide bond. So it doesn't have to necessarily, it doesn't matter how long it is, right? It just matters which residues, and it's going to hydrolyze a peptide bond. So that one was kind of the easy one. 2 is really kind of the hard one. All right, so chemotrypsin is a serine protease. Does that mean that it's going to cleave at a serine? No, what does that mean? Why do we call them serine proteases? Because of their backbone. What about their backbone? I don't know that I'd say it that way, but. So the serine residue is in the active site of the enzyme, inactive site, and it catalyzes the reaction that is going to end up hydrolyzing our peptide bond, right? So it's going to actually participate in the chemical reaction that is going to cleave the bond. So this is the residue inside of the active site that's going to make the reaction happen. Does that make sense? Okay. So even though we call it a serine protease, we really need 3 residues, 3 amino acids to make it happen. And so we call that the catalytic triad. I think that sounds kind of cool, right? But only 2 of the amino acids are actually directly involved in the reaction. So which two are directly involved? And I can scroll, oh, you know what? let me clear this. Okay, so if we scroll down, right? If we scroll down, which 2 are actively involved? His 57 and serine 195. It's kind of nice to be able to look at a picture of what's going on, which is why I gave this to you. And I know it's not so nice to look at on the copy, but at least you have something to refer to. And it's on Moodle. Okay, so what did we say? So what's the question? All right, so it depends on the catalytic active site. Only 2 of the amino acids are directly involved in the mechanism shown in the video. What are these 2 amino acids, and what role does each play in the reaction mechanism? Oh, this is a big one. This is a big one. So what role, let's talk about first his 57. What does his 57 do? Histidine removes and adds protons. That is correct. That is correct. All right. So what's the big thing that has to happen in order to prime this reaction? What's going to donate to where? Serine 195 is going to transfer what? Not the whole hydroxyl group, just the hydrogen to what? His 57. So it's really actually because nitrogen's negative, partially negative, and the hydrogen's partially positive. That's why you have that initial reaction happening. So the nitrogen basically steals away the hydrogen from our serine 195, right? Okay, and every time I scroll, I'm gonna have to clear this. Okay, dang it. All right, so we've basically stolen the hydrogen here. So we're in step 2, right? We've basically stolen the hydrogen. And so what happens next is that peptide goes into that active site pocket, right? And we know that this is specific to certain residues within the polypeptide because we have this pocket where aromatic residues can sit very, very nicely. So this is going to be specific to aromatic residues within the peptide chain. All right, so what happens with his and serine? Right, this one's our serine, and this is our his, right, his 57. So what's going to happen? When that hydrogen gets taken away, right, now what's going to happen? We have this negatively charged oxygen right here. Nucleophilic attack onto the carbon of the carbonyl. But that gets kind of funky if you have a nucleophilic attack on that carbonyl group. What if you have a carbonyl, right? It's a CH on that side, and you got a nitrogen on this side, and we started out with a double bond, right? Now we're saying that we're going to have another oxygen coming here. Is that a stable configuration? No. So what's going to change? We're going to lose that double bond, right? What happens when we lose that double bond? That oxygen becomes what? That oxygen becomes super negative, right? Okay, what else can you tell me about this configuration? What were we before? If you have a carbon double bonded CH and a nitrogen, what three-dimensional shape is this? Trigonal planar, right? Okay, what did we convert to? Tetrahedral. So tetrahedral is okay, except for this. This is super unstable. So if you are not inside of an enzyme, this would be very, very difficult to maintain. This would be very, very, very high energy. This reaction would likely not go because of a high activation energy. How does the enzyme accommodate this? It stabilizes it. How does it stabilize it? Right here. We have this little pocket, right? And that little pocket has our two hydrogens here that are partially positive. So those partial positive charges on our 2 hydrogens, one from serine and one's from another residue, from a glycine, are going to stabilize that. That's why they call it the oxyanion pocket, right? Because it's going to stabilize that. So if you have the enzyme present, the activation energy to form the first intermediate is low, right? So this is why if you're doing the reaction mechanism, you start here and you're going to have a small hump, and then we're going to end up with another small hump, and then we're going to go down instead of something like that. Right? So we're here at this very first intermediate, okay? So now what happens? Now what happens? We have this intermediate, but it's very unstable. Even though it is stabilized inside the enzymatic pocket, it's still relatively unstable. So it's not going to sit around in that form for very long. So what's going to happen? His is going to do what? So this is our his. Why they took away the labels? I shouldn't have taken away the labels. So this is histidine and this is serine, right? So what's histidine going to do? it's going to give that hydrogen back, basically, right? So now our bond ends up being lone pairs on the nitrogen, and our hydrogen goes back to the nitrogen, so then you end up forming that bond there. So what's going to happen now? What are we going to do? We're going to break this bond right here between the carbonyl carbon and the nitrogen. That's our what? That's our cleavage. So our cleavage has happened. This is our first step. That's our first cleavage event. So we can kick out that first part of our peptide, right? That's going to be the carboxy terminus. But are we done? What's the problem? We still have a piece of that peptide that is covalently linked to our enzyme, right? It's attached. So what do we have to do? We need to kick it to the curb so that we can do this again, right? So how are we going to kick it to the curb? Come on. I want to get rid of my stuff. There it goes. Can I move this? No, I cannot move that. I had this all nice. There we go. Okay, so what's going to happen? Now that we've kicked out half of our peptide, we have a whole lot more space inside of there. So what's going to come in? Water pops in. All right, now that nitrogen on his is partially positive. So what can it do now? It could steal a hydrogen, but it's not going to steal a hydrogen from the peptide anymore. It's going to steal a hydrogen from water. So this is not general. Remember, if it's water, it is specific acid-base catalysis. If it's general, that means it could be any amino acid that makes that happen. That's why they call it general. If it's specific, it's only water. I know it's kind of backwards. It kind of feels like it's backwards, but that's what it is. Okay, so now we can have nucleophilic attack. Now we have basically a hydroxyl, right? So what is that hydroxyl going to do? It's going to go in and nucleophilically attack the carbon. Oh, what kind of an intermediate are we going to form again? A tetrahedral intermediate, right? So now we have yet again, our carbonyl carbon is going to be in a tetrahedral arrangement. But what is it stabilized by? Those hydrogens, those partially positive hydrogens, right? So this is why that second hump, yes, it's higher energy than the reactants were, but it's much smaller than an uncatalyzed reaction, right? Okay, so now what happens? We've made this intermediate, but it's unstable. We don't like to stay in this state. So what's going to happen? How are we going to kick out our second product? What's that? We have to cleave it again. We have to cleave it again. But this time we're going to cleave it right in here between the serine oxygen and the carbonyl of the peptide. Now we've basically released it from serine and it can go on its merry way. And what do we have left? A primed and ready to go enzyme. But I thought this was a triad. How many different residues have we talked about so far? Two. Only two. Only two, right? So our third question, if we go all the way back up, our third question, what is the third amino acid of the catalytic triad that wasn't even shown in that video? And why is it essential for catalysis if it's not directly involved in the reaction? We went through that whole reaction mechanism and we only talked about two residues. So why is serine important? Did I put it for y'all? Yeah. Why is serine important? Why is aspartate important?
Is used when histone so that it converts
That's right. So if you look at serine, serine normally has a hydroxyl group on it. That hydroxyl group, this oxygen right here, is not negative enough to induce nucleophilic attack on our incoming peptide. You won't cut it. So what do you have to do? You have to deprotonate it. How do you deprotonate it? Well, it's kind of a chain reaction, right? Starts with our first residue right here. We have this oxygen that is going to come and steal this hydrogen from our his, right? So when that hydrogen is stolen, now we're going to look at our second nitrogen. Our second nitrogen has a lone pair on it. It's going to pick up the hydrogen from the serine. So now this nitrogen's positive, it's got the hydrogen. Now this oxygen is negative and it can perform the nucleophilic attack on incoming peptide. So the aspartate is there to prime the enzyme. Because if that oxygen is not negative enough, the reaction's not going to go. So it's called a serine protease because it's the serine that's acting as the nucleophile to attack our incoming peptide, our incoming carbonyl of the peptide, right? But it couldn't do that if this triad weren't present. So I think this was one of the ones, I think that was a lot of steps and was kind of hard to understand. So I'm hoping that going through this has kind of helped to clarify those steps for y'all. Yeah? Yeah? Okay, good. Good. Yay. All right. Y'all got questions on this one? I left you the kind of blank one. I thought you might be able to use it to just kind of go through for yourself and explain what's going on in the whole stepwise transition. Okay, can you explain the third step again? Okay, so here in the third step, right here, with the partial positive. So our nitrogen on our his, right? This is the one that is going to take the hydrogen away from the nitrogen in the polypeptide backbone, right? And so that's going to break this bond. I don't know if I could zoom in. I wish I could zoom in more. It's going to break that bond right there because the electrons are going to move to make the bond between the nitrogen and the hydrogen. So that's how you're going to break that bond. And so this is the fragment that you're going to end up releasing. Because this carbon inside of your unstable tetrahedral intermediate is not going to want to hang out in that tetrahedral arrangement anymore. Are you talking about the partial positives here on these hydrogens or the partial positive over here on the nitrogen? It's hard when y'all aren't in class. On the his, okay, okay. So once you steal that hydrogen, then that nitrogen becomes partially positive. So it's the stealing of the hydrogen from the peptide fragment. Does that answer your question, William? Good. All right, awesome. Okay. So any other questions on chemotrypsin? Good. Yeah. All right. Okay, so let's try a few clicker questions. And now I mixed them up. These are kind of from the entire chapter because we've done the whole chapter now. So some of them should be super, oh, I don't want the PowerPoint. I want this one that I can write on. The birds sound nice out today. Okay, and then I gotta get this. Okay, so we can stop that. All right, now y'all try to help me see. I mixed in a lot of these as some of them are A, B, C, D, some of them are choose more than one. So if y'all kind of help me to make sure that I'm doing the right thing, that'd be awesome. Okay. And I want to do it this way. All right. Here we go. Y'all ready? Okay. Let me do this. All right. Folic acid is a molecule that is chemically converted to tetrahydrofluorate, THF. THF is used to transfer a carbon group from one molecule to another. This is required for nucleotide synthesis and is required by thymidylate synthase. Which of the following statements is most correct? So just one, pick one choice that is most correct. Yep. No, I'll give you till 2 minutes. All right, how many, I thought we had like 51. We'll go on to the 15 seconds. At 2:15, I'm gonna call it. 5 seconds. Okay, so all of the choices are either coenzymes or cofactors. So somebody remind me, what's a cofactor? It's not. It's not. What's that? Inorganic, or G-A-N, inorganic. And then so then a coenzyme must be organic, right? But they both do what? They're both required. They're both absolutely required for enzymatic activity. Okay, so you need to figure out which one of the substances is required and then think about, could it be organic or inorganic? So those are your two kind of things that you're trying to decide between. So let's pick which one is required. Is it folic acid or is it tetrahydrofolate? Does folic acid participate in anything? No. So you just cross those out, right? Okay. So our tetrahydrofolate, is it a coenzyme or is it a cofactor? And how could you figure out just from the information provided? Any guesses? It says transfer a carbon group. So what does that imply about the molecule itself? That it's carbon-based. If it's able to transfer a carbon molecule, a carbon atom, it's most likely carbon-based. So which one would you say, coenzyme or cofactor? Coenzyme. What am I? I'm circling the wrong thing. Hello. Hello. Coenzyme, right? Coenzyme. Yes. And usually organic compounds also do have hydrogen in them. So that's another good one. Michelle, that's another good one. Okay, so what did y'all say? Ooh. So people wanted to say it's a cofactor. Yeah, there's a difference between a cofactor and a coenzyme. When we talk about coenzymes and cofactors, do you remember, it's not on this clicker thing, but do you remember the difference between a holoenzyme and an apoenzyme? Since we're talking about enzyme designations? Yeah? So a holoenzyme is what? Yes, so it has coenzyme or cofactor, right? That's attached, so it's bound. How about an apoenzyme? It's missing it, right? It's missing the coenzyme slash factor, right? So which one is an active enzyme? The holoenzyme is active, and the apoenzyme is inactive. And y'all don't worry about cell phones, it's okay. I was in, this is my embarrassing cell phone story. I was taking, I think it was micro, no, I don't remember. I was doing research with an advisor, you know, while I was in undergrad, and I was in his lecture class. I'm trying to remember what the lecture class was, I can't remember offhand. And I had just gotten a cell phone. I was so excited, you know. So this is dating me now because I'm in college and I got a cell phone. And I had programmed the Star Trek theme song to like my parents when they were calling me. So in the middle of class, it goes da 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 da. You know. My professor goes, "Well, somebody's going where no one has gone before." Like, oh, I'm so embarrassed. All right, so we said that one. All right, so we ready for the next one? All right, here we go. So Endolase, an enzyme in glycolysis, requires Mg2+. It catalyzes the conversion of 2-phosphoglycerate to phosphoenol pyruvate. This is an example of what kind of catalysis? It's not as hard as you think. It is not as hard as you think. I'm giving you 1 minute on this one. 1 minute. Okay, 5 seconds. Okay, so what did y'all say? Good. D, metal ion. It's metal ion catalysis. So what would we refer to Mg2+ as? A cofactor. This is a cofactor because it's saying it's required for enzymatic activity. Okay. That's what I said. Isn't it also general acid base? Why would you say it's general acid base? So based on the information given, right, you can only make a comment on what was given. So if I give you more detail on the reaction, then absolutely, yes, you could say that. But when we talk about the specifics in the question, stick with what's in the question. But yes, you're right. Okay. All right, so now, okay, a little bit of kinetics. A little bit of kinetics. I'll give you a couple of minutes on this one. Carbonic anhydrase is a vital enzyme that maintains the buffering capacity of blood. It uses 2 substrates, CO2 or HCO3. Using the table, which would be the best choice for a substrate and why? I'll give you like 3.5 minutes on this one. Okay, about 10 seconds. Okay. All right, so I want to see kind of what y'all said. So we're kind of torn between A and B. So you picked the right substance. It is CO2. You are correct about that. It is CO2. Now let's talk about, what did you notice when you were reading these statements? Did you notice that every single statement is a true statement, right? For CO2, does it have a specificity constant that is higher than HCO3? Yes, so what is the specificity constant? What does that refer to? Kcat over Km, right? What does a specificity constant tell us? Maybe let's start with what is Kcat. Let's start with the individual components first. What is Kcat? It's the rate limiting step. That's true. That's true. It is the rate limiting step. Yep, it's the turnover number. So it tells you at saturating concentrations of substrate how fast your catalytic activity will be. So at saturating concentrations, max catalytic activity. That's where the cat comes from, catalytic. Okay, if that's Kcat, what is Km? It's the Michaelis-Menten constant, but what is it? If it has a unit of m, it must be a concentration. A concentration of what? Look at the units, always give you tips. Always look at the units. It's the concentration of the substrate where 1/2 Vmax is reached. That is correct. So it's half of the maximum rate of the reaction. So tell me, for an optimal enzyme, do we want Km to be high or low? We want a low Km. That's very good. We want a low Km. How about a Kcat? Do we want a high Kcat or a low Kcat? We want a high catalytic activity. So you want high Kcat. Okay. Now, our specificity constant is going to take into account our Km and our Kcat. So if you look, they gave you the formula in the table, right? So it's Kcat over Km. So what's going to be the optimal specificity constant if we want a high Kcat and a low Km? Do we want our overall specificity constant to be high or low? We want it to be high, right? And when you're taking into account what's the best substrate, you have to take into account your Km and your Kcat. Each one will give you a piece of information, but they don't give you the total. They don't tell you all the parameters of your enzyme substrate interaction until you get to that specificity constant. So what did we say? We said between A and B. So what do y'all think now that we've talked about that? Can you just base a decision based on Km, on the Michaelis-Menten constant? No, we want to base it on the specificity constant. So it should be A. It should be A. Okay? Does that make more sense? I'm telling you, if you define what is Km, what is Kcat, if you understand the individual pieces and look at those units, it's going to tell you where they are, right? Numerator or denominator, and you're going to be able to figure it out. So work backwards and look at the pieces. And that's all the time that I have. Shucks. Hi, somewhat. Okay. Any questions? Everybody okay? So next time we meet, chapter 8, section 1, and I am like this close to finishing the exams. I'm on the last discussion question. So I will work on it to get it out to y'all today. It was supposed to be done over the weekend, but but then they closed school. So that was quick of a lecture. Well, that was an hour, right? Is my time off? Y'all want to go again?
Have a good day.
Y'all too. It didn't feel like an hour. That's because it was so much fun. That's because biochemistry is amazing and so cool. Yes, yes, our next test is scheduled for next Wednesday. All right, if y'all don't need anything on Zoom, anybody got any questions on Zoom? I'm happy to answer them. Have a good rest of your Monday.
Dr. B, can I ask you a question?
Hi, you too. Okay, I'm gonna go ahead and stop. Oh, maybe. I get to the end and then I can't make it stay. Okay, end.